Dear friends, I am back after a long time, and this program is again a coffee time with Euclid program. I have a cup of coffee, of course. It's a Nescafe. You can see the cup. I think I'm holding it in the wrong direction. Oh gosh, I am so bad at these kind of things. Anyway, I have a cup of coffee. I have some biscuits in my hand, so don't mind me sipping one. Today I'm going to talk about first two new books which I have bought in Euclid's geometry, and that you can have new books coming out in Euclidean geometry in 2025 or 2024. It's well worth the wonder. People think that Euclidean geometry is finished, but I came to know through these books that there are journals which publish results on Euclidean geometry. It may be just a mathematical curiosity now, but that it is a lot of fun because Euclidean geometry, the proofs that you do in Euclidean geometry, that approach is called synthetic geometry. Synthetic geometry is something where you are not using the method of coordinates, where you are arguing logically by looking at the diagrams and all those things. You have certain axioms and to base your ideas on, and so forth. So that is the way Euclid proved the things. So that is what we call synthetic geometry, and then you have the coordinate geometry. So here I have these two books, Lectures on Euclidean Geometry by Paris Pamfilos, a Greek of course. The first part is called Euclidean Geometry on the Plane. Maybe I should bring it near to this. We will have one discussion completely about these books on a separate coffee time with Euclid, and that would be more detailed. So today I am not going to go into detail but show you a large number of books. Okay. I wonder why this beautiful subject is not suddenly stopped after school. You have coordinate geometry, you seem to forget the synthetic method as it is not valuable, there is no results beyond this. For example, in school you never learn Siva's theorem. Siva's theorem is a wonderful theorem. It tells you that if you take a triangle ABC and from A you draw a line to BC, so you take points D, E, F on the respective lines, BC, AC and AB, and join A to D, B to E, C to F. And these lines are concurrent if AF by FB, BE, BD by DC, and CD and CE by EA. If you take these ratios and take their products, that product would be 1. And if you find a triangle where when you put 3 points and join these lines and the product of these ratios are 1, then they must be concurrent. So it's an if and only if characterization of concurrency of 3 lines. Now, if these were midpoints, and so each one of the parts of the triangle which the points have 3 points have divided, they are all equal, so their product is all, so they will cancel the top and the bottom. Each ratio would be 1, so the product is 1, and that is what your theorem is about, that medians of a triangle are concurrent. Of course this is better explained in a board, and that will be done because this here is a celebration of elementary geometry, rather Euclid's geometry. So here is the second book. It's on circle, measurements, transformation, space, geometry and conics. Space geometry means 3D geometry. Please understand that 3D geometry is something which we do not do much. We never teach our students actually, unless possibly in engineering. When you do engineering drawing, something must be done, or when you do computer aided design, something must be done. I have no much knowledge about that, even though I stay in I'm a part of a system where such courses are on completely. but since I'm from more from the hard sciences, and so it's I am really not a part of that. So, but it's very unfortunate that in mathematics courses in colleges, you don't bring in geometry of of solids, and I think this is a lacuna in the system of our education. That if we teach these kind of things, it will be a waste of time. Nobody would get a job, and that is why it is needed to have mathematics degree which is more purely focused, who wants to be in the subject, and which will have another degree which will have a more market component, subjects which are more market oriented like statistics or probability and statistics. That doesn't mean that these people won't be learning some probability or probability, for example, or maybe the people who are going into the more math oriented stream learns more measured theoretic based probability, and here you may not stress much on measured theory but more on the statistical tools, etc., and all these things. So there can be two streams. You may call it pure and applied, or you call maybe mathematics, or what, maybe market driven mathematics, whatever you want to call. Some names can be given. One may give a science degree and another might give a tech degree. I think there's a BTech in mathematics and computing type of thing in IIT Delhi. So instead of giving an MS degree could be given to the math one which is more math oriented. So if you take a 4 years degree, a course based on these two books can easily be put in. So that's what I'm trying to tell you. Now, for having fun, I have two books here. I'll show one by one. This is a book published by Springer, written by Megan L. Dillon, called Geometry Through History. It's a pretty recent book, and it starts with basic Euclid geometry and goes on to ultimately everybody starts talking about the fifth postulate, which essentially tells you that given a straight line on a plane, there is a point outside it, and through that point only one line can be drawn which is parallel to this line. If you just think about the plane, 2D plane, two-dimensional plane, I think there isn't any other choice. But if you just consider what the type of things Euclid was doing, but there can be a lot of questions which can be put onto this axiom. It cannot be proved directly from the other axioms. So it appears that it is, and also it doesn't not so obvious the way Euclid wrote it, of course. But the whole idea is that if I defy this axiom, can I build a geometry or build geometries which are absolutely consistent logically in the sense which Euclidean geometry is, that there are axioms and those geometrical properties will follow, or the results or theorems will follow from axioms. So you can create geometries which is based on throwing away the fifth postulate. So a lot of stories in all these geometry books are based on the fifth postulate. There's a whole book I'll show you essentially written on the fifth postulate. And not one older and one modern. Okay. And here you will see a lot of things. Then a very good part of this book discusses Hilbert's Grundlagen, means Hilbert's new foundation of geometry. So Hilbert gave a new kind of axiomatic system. For example, if you look at the first proposition 1, book 1 in Euclid, what does it say? It says that if you are given a line, construct an equilateral triangle of that line. And in your modern terms, of each side would be of that length. So take those two endpoints, say A and B, put your compass on A and take AB as the radius and draw a circle. And then take BA as the radius and draw a circle. So you know there will be 2 points exactly, and when you see the photo, sorry, the diagram, drawing, there will be 2 points exactly where it will intersect. There is no other choice. You can draw as many as you like, you will not find, but that doesn't exhaust, that doesn't logically exhaust every possibility. Now you take one of the intersecting points and join them with the points A and B, and immediately you will understand why it is an equilateral triangle, because all the other two sides are equal to AB because they are the radius of those respective circles. So we now, what you have done, you have drawn a circle with the same radius but two different centers, right? So which are and those centers are lying on the on a straight line. They are connected. So now there's a question which Hilbert asks. For example, if you are a very purist, you can ask that you may keep on drawing this picture and always you will get exactly 2 points. So it's a picture based proof. It doesn't anyway eliminate, you're never eliminating the situation that such a thing can never happen. If you may keep on drawing, that doesn't exhaust the all possible possibilities of lengths, because their lengths are real numbers, so you can't exhaust it. You might think that this is too much of a purist. If you are thinking that this is too much of a doing, then you would be doing good in applied mathematics or physics, or even engineering. But if you think that no, here's some point, then what should be done is to bring this thing that if circles intersect in this manner, they will intersect in exactly 2 points. Can that be an axiom? If that is an axiom, then of course what you would say and do is true, right? So that's the point, because I can have a circle which can, two circles can always touch at a point, but if you are having a circle, two circles drawn based on the same diameter, right, on the same radius, sorry, I know, and the centers are lying on the ends of the same radius, then only exactly such 2 points will come. So those kinds of for these kind of issues, he developed new systems of axiom, and that is discussed very well in this book by Megan Dillon. She tries to also discuss non-Euclidean geometry, hyperbolic geometry, etc., and comes ultimately into algebra. Because I always say that possibly we would, and also talks about projective geometry, which is very good. You will always understand mathematics better that if you know from the very outset that algebra is geometry and geometry is algebra. So, but geometry is too much of an important thing, because in mathematics, I strongly believe that most of the time you need visualization. You need to see how things are interacting, see figures. In my own area of optimization, I have been always drawn towards the geometric conditions. In my papers, you will always, or books or talks, I'll always be talking about normal cones, always be talking about tangent cones, because these are the vehicles through which things happen. You represent optimality. For example, Lagrange multipliers. Lagrange multipliers have a role in the building of these geometric objects. So in optimization, so geometric visualization is extremely central to mathematics, and that should not be done away with. So Euclid obviously doesn't know that I'm drinking coffee in his name. This is a book I recommend to each and every library, in schools, in colleges, in universities, in IITs, and everywhere. IIT possibly has it. Geometry by its history. Now it's a paperback version, and I had some money in my research grants to buy it. This book is a huge amount of fun, and you should not be devoid, you should not strip yourself of the fun this book gives you. It is about Euclidean geometry. It starts with the elements of Euclid. It starts with things which happened after Euclid. For example, the result of Siva, the result of Menelaus, which are related to incidences, means how, whether three lines are concurrent or whether three points are collinear. So it's an incidence property, points on lines. So these properties, called incidence properties. Incidence properties give rise to what is later on called projective geometry, and that is very, very important, and we will have a chance to speak about it in this year-long celebration of elementary geometry. So there is many interesting theorem like Euler's 9-point circle, Michel's theorem, Steiner's circle theorem. There's a whole lot of things. You can see the book filled with diagrams, black and white diagrams though, but for a geometry lover this is an very good time passing occupation. There is the famous Morley's triangle. So here is this famous Morley's theorem. So what you have done, basically you have trisected three angles of a triangle. Basically you can say that, trisecting cannot be done, impossible by compass and all, straight edge. Forget those kind of things. Trisecting, you have seen the angles and you have actually divided it in that way. If you look at this trisection, so you will see these 3 points come up, right? Basically these 3 points actually form an equilateral triangle, and that's the Morley's theorem, and that's amazing. Can you believe that you have done this? And it's not so simple to feel that this gives you an equilateral triangle, because these 3 triangles, angles A, B, C, they are not the same angles. They are different angles, they have different values, and from there you can generate equilateral triangle in this manner. Is something still startles me, and that is why Euclidean geometry is always so fascinating, and it would remain. So this is one of my favorites, and I always enjoy with it whenever I travel. I just carry on seeing the various results. There are theorems which has been given by the great mathematician of the 20th century, Paul Ehrthus also, and there is a lot of thing about spherical triangle, trigonometry. It comes even to Euclid, this differential geometry, analytic geometry. A lot of things has been done. Means it's a wonderful compendium. Those who love geometry, you can spend hours and hours. It comes even into linear algebra, because there is, again I am telling you that you will know mathematics, you will appreciate mathematics much more if you get into the subject by knowing at the very outset that algebra is geometry and geometry is algebra. So it talks about famous theorems like Poncelet's theorem, which are again related to projective geometry, and it also talks about conic sections. So here is my favorite book among my stocks here. I do not know about the 2 books which I have just bought, which came to that 2 days back, and I really have to have a check on it. This book, published by Dover, possibly one of the best book written in a historical way about non-Euclidean geometry. Geometries that have developed by throwing of Euclid's 5th postulate. You cannot call it a modern book, it's more historical. It was written in 1906 by Italian geometer Roberto Bonola. I bought it long back from College Street, from Sharad Book House in College Street actually. There's a famous, I will call it the science bookstore of India. So here it starts with the 5th postulate. The first page has the 5th postulate. So let me read that 5th postulate for you. And then there is a beautiful section on people's attempt to prove the 5th postulate. Ultimately unable to do it, because you will somewhere use the 5th postulate. So if a straight line falling on 2 straight lines make the interior angles on the same side less than 2 right angles, the 2 straight lines, if produced indefinitely, meet on that side on which the angles are less than the 2 right angles. There is in this a, a germ somewhere of the fact that sum of three angles of a triangle is 180 degree. Because if you have two straight lines, you know parallel lines, they have the interior opposite angles are some 180 degree. But if these two are not 180 degree, he says that it will actually, the lines will actually, if they produced, these are non-parallel lines, will meet at some point. So basically, then the sum of the three angles would be 180 degree. So that gap of that you have from 180 would be covered by the other angle at the intersection. So this is there is a clue there. That is the way I think about it, but may not be that's the best way to talk about it, because this has an equivalent form called the Playfair's axiom. The Playfair's axiom says that given a straight line and a point outside it, one and only one line can be drawn through the point P, and that is parallel to the given line. If you take the Euclidean plane, which is moving away in all directions infinitely, see, a lot of things come in mathematics which you use, but that particular subject, because the infinities were not discussed by Euclid in a geometrical sense. Of course, he proved the infinity of primes, that primes cannot, you can just keep, they will keep on appearing in the number list. But it's very important to appreciate the fact that somehow if you close your eyes and think on the plane, vast plane on all sides, you're moving, whatever direction you keep on moving, you will keep on beyond the plane. That's essentially the idea of the plane. Such an ideal plane doesn't exist. You will never find that, because we live on a spherical body. So if we just keep on actually moving straight and could get out of the world, so when you get out of, when gravity doesn't matter for you, you will just go straight into space, right? So this book actually gives a historical thing, and it's a pretty funny proof, and a lot of people are trying to do it. Shakeri, Lambert's proof approach, and many people are trying to do it. And then comes Bolai, Nicholas Bolai and Lobachevsky, who actually makes a lot of progress, that they build geometries by telling that Lobachevsky says, okay, I am in a situation, I am not talking about Euclidean plane. I'm in some situation, some space. So I have a line and a point outside it. And I say, okay, more than one, maybe two parallels, line can be drawn parallel to this line. If I have this, can a geometry be developed with theorems and results which can be consistently proved with the fifth postulate now replaced by this, Euclid's fifth postulate? And that is why those geometries, which are logically perfect, are called, I mean, their approach is exactly like Euclid, but the fifth postulate is changed, are called non-Euclidean geometries. These are never taught in our curriculum, but later on in my own research I have seen that we had used a certain kind of distances called Bregman distances in convex optimization, and these were non-Euclidean distances. But you use that term, but you remain I had remained uncomfortable, because we really have very less understanding of non-Euclidean. Of course, if you take a sphere, now in 2 points, the shortest distance between them is a geodesic, which is lying on the great circle on which these 2 points lie. So that is not a straight line, of course. So you cannot measure it just like you do on the real line. It's on the plane. So this is a non-Euclidean world. So the world is essentially non-Euclidean. Space and time are curved. They have curvature due to gravity. Gravity doesn't appreciate Euclid. Gravity appreciates the non-Euclidean world. But in our mind, in our local system, in our local thing, basically I am sitting at a point. In my local area, this local area I can feel as flat. So everything that Euclid says works. And that is why Euclidean geometry is so helpful. That is something you have to keep in mind. It's basically, here is a sphere, but I cannot do really Euclidean geometry even around that point on the sphere, because things are curved. So essentially, Euclidean geometry is the geometry that I do on the tangent plane that you draw at that point on the sphere, the two-dimensional plane. So, but however, in our own view of this part that we live, if if the but if we can take a very small part of the sphere and we can actually map it, we can have a homeomorphic mapping, a bijection to a open set in R2. So an open set in R2 is almost it is a model of R2. So that way it tells you that okay, you can do with your Euclidean stuff in a very small region. You are pretty okay, you are a part of a plane. You can think of yourself to be a part of a plane. Essentially it is the same thing. It just tells you that the tangent in a very small zone does a more or less good job of approximating the function, the space itself. The tangent approximates the space, and that is why you can, because the tangent plane is a Euclid's plane, and so in a very local sense, Euclidean geometry always works. So in a practical sense, Euclidean geometry is very okay, but if you look at the real physical sense in a bigger scale, in in a very proper sense, then it doesn't, it cannot be. There is no such thing as, there cannot be anything like Euclidean geometry or Euclidean plane. But of course, the tools that we create by our imagination does a lot of help to real applications, and that is why it's so important. And that point has to be, put through. So this is a book I will not recommend, but libraries might have it. Some people who are interested in the subject may have a look at it, because the reading might be a little archaic because it's too old. The book that I would suggest for those who doesn't care much about axioms and all those stories. They want problems, they want solutions, they want fantastic theorems. Here there is a theorem called the butterfly theorem. There is a college, it's written by an algebraist, I. Martin Isaacs. He also has a very good book on abstract algebra. It's called Geometry for College Students. And Geometry for College Students, this book is filled with fantastic results. And let me try to find the butterfly theorem. Let me try to just go through butterfly theorem, page 105. Let me see what does this thing says. So here is the picture of the butterfly theorem. You see it's written butterfly theorem. And let me read it. So suppose the chords PQ and RS of a given circle meet at the midpoint of another chord AB, right? So see the diagram, any one of the diagrams where you have the chord AB, M is the midpoint. Basically, you through M, you are joining, you can extend the line. So through M, two other chords are passing, right? Namely PQ and RS. If X and Y are the points where the X and Y are the points where the lines PS and RQ meet, means here you can have a look again. So X and Y are the points where PS and RQ meet. Carefully have a look. So they claim that XY is also equal to MY, that M is also the midpoint of XY. This is called the butterfly theorem, and that's quite lovely, and I really like it. And it's not, proof is not so straightforward, but it just uses ultimately similar triangles. You can learn a lot of things here, like cross ratios, and because these are all linked with projective geometry. And it does certain important results of projective geometry, and it gets into constructible numbers and the squaring of the circle and all these things. It talks about linear operators, ultimately the dot products, and so linear algebra is deeply linked. But modern Euclidean geometries always has a linear algebraic flavor. It has to there is no other choice. Because you're in two dimensions, so it's vectors and hence linear algebra. So it's a very good discussion about Siva's and Menelaus's theorem, and it doesn't care too much about your axioms, etc. And it just starts from the very basic things of parallelograms, angles, parallel lines, triangles, some basic theorem, and goes up the ladder. So this is one of my favorites too when it comes to really teaching something. So you don't boggle the student down with your the fifth postulate, but you just go ahead and do something which is fun. The last but one book of today's series is Axiomatic Geometry. This book is essentially about the Euclid's fifth postulate, the parallel postulate. The whole book essentially is about a parallel postulate, and I will myself I'll look at it deeply and then do a kind of review, more detailed review for you. For those who are interested in geometry, it's called Axiomatic Geometry. So you can understand that the fifth postulate plays a major role, that even on the plane you can create zones where you can have geometries where fifth postulate can be violated easily. For example, the Poincaré disk. We will talk about them in more detail. We are not going to talk about it here because there are a lot of geometries that can come out of the throwing away of the fifth postulate. One geometry is due to Lobachevsky, called Lobachevskian geometry. One is a spherical geometry, the Riemann's geometry, and so on and so forth. So let us not get into but this is written by John M. Lee. John M. Lee is a very, very famous mathematician who is a great writer of books. My coffee is it has got cold actually. So maybe I'll forget it for the moment. John M. Lee has 3 books. Topological Manifolds, which has a very, very good section on topology, point set topology. He has a book on smooth manifolds. Physicists need smooth manifolds up and down continuously. Then he has Riemannian manifolds. 3-volume book, which I have, and I'll share with you sometime, but this is very advanced level mathematics. Now, when you study, our last book is that about geometry of conics by 2 Russian mathematicians, A. Zaslavsky and A.V. Akopayan. So, this book, which is published in the Mathematical World version in one Mathematical World series by AMS, American Math Society. It's called Geometry of Conics. You can see this is how an ellipse is drawn, right? So the goat is eating up an area surrounded by an ellipse. Now this book, when our own idea of conics comes from our study in our 11th and 12th standards in the high school of analytic geometry, coordinate geometry. We study parabola, hyperbola, circle, all kind of things. But can conics be studied in a manner which is just like Euclid, the synthetic manner? So here is the one which we do. So here is the one where everything is being done in the synthetic manner. In these 2 books, the first 2 books that I showed in this volume 2 of lectures on Euclidean geometry, conics are discussed in detail, not in this detail, but to a great extent, but using the synthetic manner, an approach which I love. So here you see, you can always see, it uses similarity of triangles, you see here. What is it called? Here. Similarity of triangles always plays a fundamental role in Euclidean geometry. It is, sometimes I feel that is actually playing the game. Everywhere that is the game. Somehow, where triangles are involved, somehow similarities of triangles has to be used. I'll speak more. For example, look at this chapter, one of the last chapters, Euclidean properties of curves of second degree. So these are not actually taught. When you're taught, you miss a lot of things about conics. When you here, they are also giving you certain links with the coordinate aspect, but when you do not look at the synthetic part side by side, you miss a lot of information about conics. You're just solving the equation, you're bothered with that algebra. So there is this saying I read somewhere in some book, it must be with me, that the devil comes and tells the mathematician, I'll give you a tool by which you can calculate everything, but for that you have to give up your soul. Take algebra and give up geometry. So that is what has happened to our education system also in mathematics, that it takes away our soul and mathematical soul, and that is the result of which a lot of things are not done actually. We hardly have information about those structures. A person would be more mathematically sophisticated if these things have been taught at least till the first year level, at least for a math student. For 11th, see, I think even from the 12th, 11th, 12th level, mathematics education has to be divided. Calculus may be there for both the things, which is too basic. So very basic things has to remain, coordinate has to be there, but a large part can come, which is of this geometry, along with the coordinate part, the geometry that for example, in the conic part, you can have some synthetic aspect, some solid geometry can come in the in the part where you are giving mathematics more as a pure math degree, a pure math version rather than a more market oriented version. I think that division has to start now from the high school, because then it will be clear. The mathematics has become so vast that it's not possibly a good idea to give everybody a uniform teaching of mathematics even at the high school level. I'll strongly advocate two different pathways, and then they can choose. Of course, you can change the path later on also. There is no harm in it. But two different pathways are better, because at least people can choose what they want to learn, because there's so many things to learn and they have so limited opportunities that's not a fair deal. So I hope you have seen a lot of books. Next one is in the department. It will be the long review of linear algebra by Axler. It will come up very soon again. So thank you once again, and please enjoy your evening.